The James Webb Space Telescope, often described as a powerful magnifying glass, offers unprecedented clarity in revealing the intricate details of distant planets. Recently, the JWST set its sights on a remarkable target, K2-12B, an enigmatic exoplanet that has captivated the attention of astronomers and researchers worldwide. Initial observations of K2-12B sparked a wave of excitement within the scientific community. This celestial body was no ordinary planet. Not only did K2-12B exhibit the presence of water vapor, a potential indicator of habitability, but it also contained a molecule that arose deep intrigue, a molecule often associated with biological processes on Earth. Could this be the momentous revelation humanity was waiting for, the confirmation of extraterrestrial life? In this exploration, we'll delve deeper into K2-12B, uncovering the scientific challenges and far-reaching implications that could reshape our understanding of the universe. Let's embark on an investigation of the first tangible image and detailed atmospheric analysis of K2-12B. K2-12B, located 120 light-years away, is a super-Earth within its solar system. Distinguished by its classification as a sub-Neptune, it represents a class of planets unlike anything in our own solar cosmic backyard. This planet is larger than Earth but smaller than Neptune, defying conventional planetary categories. This unique status presents a considerable challenge for scientists trying to unravel the mysteries of K2-12B. While rocky planets like Earth and Mars serve as benchmarks for habitability hypotheses, and distant gas giants like Jupiter and Saturn offer tentative comparisons, sub-Neptunes, especially ones like K2-12B, have no familiar counterparts nearby and remain a profound enigma. The data available so far suggests some fascinating theories. For example, K2-12B orbits within the habitable zone of its host star, a red dwarf called K2-18, raising the possibility that its surface may harbor liquid water similar to Earth's oceans. It is crucial to note that K2-18b's orbit around its host star is much closer than Earth's orbit around the Sun. While 1 astronomical unit, AU, represents the average distance between Earth and the Sun, K2-18b is only 18 cents away from its star, even closer than Mercury is to our own Sun. This proximity means that a year on K2-18b lasts only 13 Earth days. Fortunately, K2-18b's host star, being a red dwarf, emits significantly less heat than our Sun. This prevents K2-18b's surface from being completely scorched, unlike what would happen if it was so close to a Sun-like star. In fact, K2-18b's host star's lower luminosity has turned out to be a benefit, as it has allowed signs of vaporized water to be detected in the planet's atmosphere, a groundbreaking discovery that suggests the presence of biological signatures similar to those found on Earth. This discovery further increases the scientific interest in this exoplanet. It is a revolutionary moment in astronomy, indicating that the chemical precursors of life may not be unique to Earth. The fact that methane decomposes rapidly under solar radiation added even more excitement to the findings. The JWST also detected carbon dioxide, a more common atmospheric component. However, the combined discovery of methane and CO was a slow and methodical process, requiring immense precision. More importantly, dimethyl sulfide, DMS, unlike methane, is not commonly found in Earth's natural environment outside of biological activity. It is a molecule produced exclusively by biological processes. This finding is particularly intriguing given that K2-18b orbits a red dwarf star, a class of stars known for intense radiation and often considered inhospitable to life. However, K2-18b defied those expectations. This is crucial because, on Earth, DMS is only produced by life, mainly by microorganisms in our oceans. It is known to be a reliable biomarker if detected in a planetary environment, as predicted by theoretical models. It is therefore essential that the planet receives a similar level of radiation and resides within the habitable zone of its star system, where temperatures are neither too hot nor too cold for liquid water to exist. Provided there is a stable atmosphere, K2-18b could have temperatures comparable to those of Earth. Although its atmosphere is dominated by hydrogen, which would make its oceans slightly warmer than those of our planet, the proximity between the star and the planet creates a gravitational companionship. This closeness, paradoxically, prevents surface water from evaporating entirely. This detail is of great importance, especially in light of recent research suggesting that surface water could be a distinguishing feature of exoplanets like K2-18b. Stay tuned, because we will soon go into revealing details about the mystery of the Hyanic worlds. In 2021, astrophysicist Niku Madhusudhan, known for his possible detection of DMS in space, proposed a new category of exoplanets in a fascinating paper published in the Journal of Astrophysics. These are sub-Neptunes cradled beneath a thick, hydrogen-rich atmosphere. Mattis has chosen to call this new class Hyanic, a name that suggests a mysterious, unknown nature, hinting at watery depths and alien environments unlike any we've encountered. If these water giants exist as theorized, they will be radically different from anything we have ever seen. Although they could be up to 10 times the mass of Earth and twice its radius, they wouldn't be scorching furnaces of steam. Yes, they would be incredibly hot, with temperatures approaching 200 degrees Celsius. What would define them, however, is an astonishing feature, a colossal layer of water that could represent up to 90% of the planet's mass. This vast ocean, at least in theory, could harbor the potential ingredients for basic microbial life. These dense atmospheres would trap heat from the star, allowing liquid water to exist over much wider range of orbital distances compared to rocky planets like Earth. Sub-Neptunes are relatively common across the galaxy. Hyanic worlds benefit from this extended habitable zone. This makes them ideal targets in the search for life beyond our planet, especially since larger planets are easier to detect from far distances, making them prime subjects for next-generation telescopes. Dr. Madhusudhan's team used the revolutionary James Webb Space Telescope to observe K2-18b, a possible alien world. This tool could be crucial in our search for extraterrestrial life. But there is a challenge. Even with advanced technology like the James Webb, detecting these ocean worlds remains a difficult task. The key to unlocking the secrets of K2-18b lies in a meticulously planned observation, requiring a total of 5 hours divided into 2 separate observing periods. K2-18b played a crucial role in a celestial event known as a transit, during which a potentially habitable world passes directly between us and its parent star. James Webb captured the light passing through K2-18b's atmosphere during this transit. The beauty of this technique lies in the unique fingerprint that starlight carries, a kind of universal language that reveals the elemental composition of the material with which it interacts. By separating the light into its individual wavelengths, much like how a prism breaks down white light into a spectrum, scientists can analyze this fingerprint to identify the molecules present in the planet's atmosphere. If specific wavelengths are missing from the final spectrum, it becomes an important clue in understanding the chemical composition of the distant world, allowing researchers to form a more complete picture of this alien environment. The continued exploration of K2-18b holds profound implications for our search for life elsewhere. If the presence of dimethyl sulfide is confirmed, it would represent the first detection of a biosignature on an exoplanet, an achievement that could redefine our place in the universe. The possibility that microbial life might exist in warm oceans beneath thick, hydrogen-laden skies is not only scientifically revolutionary but also emotionally powerful. It would suggest that biology is not a singular miracle of Earth, but a natural consequence of chemistry and physics that plays out across galaxies. In the years to come, telescopes such as the Nancy Grace Roman Space Telescope and proposed missions like LUVOIR and HABEX may follow up on Webb's findings, targeting exoplanets like K2-18b for even more detailed observations. The dream of finding life beyond Earth may not be centuries away. It could be just one more transit, one more atmospheric fingerprint, one more signal from the deep universe. As interest in K2-18b grows, so does the ambition of scientific teams working across the globe. Each observation of this sub-Neptune world brings with it not only more data, but more mystery. Could we truly be witnessing the first signs of life beyond Earth, concealed beneath the thick, hydrogen-laced skies of an exoplanet orbiting a quiet red dwarf? The detection of biosignature gases such as dimethyl sulfide, if verified through future studies, would mark one of the greatest turning points in the history of science. For decades, the search for extraterrestrial life has relied on indirect methods, hypothetical models, and speculative conditions. K2-18b changes that narrative by providing a real-world case study, an actual planet where life might exist, not in fantasy but in reality, governed by the same chemical principles that define life on Earth. However, we must be cautious. While the presence of methane and carbon dioxide is compelling, and DMS raises fascinating possibilities, these molecules alone are not confirmation of life. It is possible that unknown geological or atmospheric processes on sub-Neptunes could produce similar signals. That's why scientists emphasize the need for repeatability, detecting the same spectral patterns across multiple transits, at different orbital positions, and under varying stellar activity. Only by building a consistent, reproducible dataset can researchers move from speculation to evidence. This brings us to the critical role of spectroscopy, the science of analyzing light. When light from a host star passes through a planet's atmosphere, Certain wavelengths are absorbed by specific gases. These missing wavelengths appear as dark lines in the spectrum and act as fingerprints, allowing astronomers to identify which molecules are present. In the case of K2-18b, the fingerprints of water vapor, methane, carbon dioxide, and possibly DMS are becoming clearer with each observation. Yet even with the James Webb Space Telescope's unparalleled sensitivity, such measurements push the boundaries of what is technically feasible. The data is faint, and the signal-to-noise ratio must be carefully managed. Background light from the star, thermal noise from the telescope, and interference from cosmic rays must all be filtered out to isolate the desired atmospheric signature. It is a painstaking process, requiring the coordination of computer models, machine learning, and physics-based simulations. In spite of these challenges, the payoff is extraordinary. If K2-18b proves to be a habitable world, or even one teeming with microbial life, it will redefine not only astrobiology but also humanity's philosophical understanding of our place in the cosmos. The idea that life is a universal phenomenon, not limited to Earth but perhaps common on water-rich sub-Neptunes across the galaxy, would change how we look at ourselves, our history, and our future. It would also raise new questions. What form would such alien life take? Would it resemble Earth's microorganisms, or would it be something entirely different, adapted to an atmosphere dominated by hydrogen, swimming in oceans under high pressure and dim red light? Could it evolve into complex multicellular organisms over geological timescales? These are questions we may one day be able to answer, as observations